So today we have the honor and pleasure to have Céline Lichtensteiger again to talk to us about nanoscale ferroelectrics.
Okay, so good morning everyone. It's good to see that so many of you still made it this morning. I know that it has been 2 very intense weeks, very exciting topics, and I hope you are still a bit awake for today's lectures. So my topic is nanoscale ferroelectrics. I will try to make it as easy or as simple as possible. It's quite simple actually, and so if you think it's not, please interrupt me because that means that I'm just not explaining it well enough. So ask questions, do not hesitate to ask questions. So nanoscale ferroelectrics, nanoscale. So 2 days ago I gave a lecture on PFM, on scanning probe microscopes. And so now let's have a look at what we can do at the nanoscale, but in ferroelectrics. So nanoscale, let's have a look at the scale. Around us we are in the meter scale. So here you see, I don't know if you see it so well, but this is in principle a nice picture of an STM. And so just to show you the size, if you go down to the tens of centimeters, here you will see if you remember the scanner of so the piezoelectric tube of the STM, and that will be the scale of the hand. If you go lower 1 centimeter here below this scanner, you see the tip holder, and you start to see the details of the skin. If you go to the millimeter, you can start to see the probe where the tip is attached, and you see more details of the skin that start to look a bit ugly. To the micrometer size, you see the end of the probe, and you see how sharp the tip can be, and you start to see the size of the cells of the immune system. Here, this is an image of the wing of papillon, butterfly. Yes, thank you. And okay, a bit more detail. So we are at the microscale, hundreds of nanometers. You see that you get even more and more details. Tens of nanometers, and now the nanometer. Okay, so we are now at the nanoscale, and everything looks different at the nanoscale. And this is true as well for ferroelectrics. So just to put everything in place for everyone, ferroelectric materials are very interesting because this is a class of materials that are among the piezoelectric materials, meaning that when you apply a strain, you get a voltage, or when you apply a voltage, you get a strain deformation. They are also powerelectric, meaning that their polarization will depend on the temperature. And of course, they are ferroelectric, meaning that their polarization can be switched. And once you remove the voltage to switch the polarization, it's stable. So you have a reversible, non-volatile polar state. Okay, so ferroelectrics are fun at the nanoscale also. And why is it interesting? Because nowadays, there are already many applications that use ferroelectrics, and more specifically ferroelectric oxides at the nanoscale. So here are just a few examples. They are used for the high dielectric constants as multilayer capacitors or gate dielectrics. They are used also for their piezoelectric properties as transducers and actuators, for their powerelectric properties as infrared detectors, for their nonlinear optical properties as electro-optical modulators or frequency doublers, and for their remnant polarization as non-volatile random access memories. So you've seen already a lot of examples. So today I will just give a few reminder or a few examples why it's interesting to have this ferroelectric at the nanoscale. So what is very important, for example, for devices, is the field effect. So the field effect is the modulation of the electrical conductivity of a material by the application of an external electric field. So it can be used in semiconductors, Schottky diodes, or field effect transistors. Field effect transistors can be made by metal oxide semiconductors, junction gate field effect transistor, metal semiconductor field effect transistors, or ferroelectric field effect transistors. So this is a very nice work showing you how it works. So here you have a PZT thin films on top of LSMO semiconductor. And so the idea is that by switching, the quality is not so good, I hope you can still see it, but by switching the polarization, what you do is that you will induce a change in the resistance of this LCMO layer. And so this can be, this is a demonstration of a PZT used as a ferroelectric gate, LCMO used as a semiconductor, and the modulation in this work of the conductance was by a factor of 3, which at the time was already quite good. What is important also, what you learn from this work is that it's very important to see what happens at the interface. And now this can be used also as non-volatile active memory elements. And so one example, so this image here is showing you a device that was actually in one of the previous PlayStations, where the memory element was this ferroelectric PZT thin layer surrounded by these electrodes. So you see that, okay, we worked with nanoscale ferroelectrics already, but the interfaces and the electrostatic boundary conditions become to be more and more important. Another nice example from actually our very nice organizers is this device of ferroelectric memory store. So the idea was to use barium titanate, just 2 nanometer layers of barium titanate with 30 nanometers of LSMO, and with some pads on top of it of cobalt and gold pads. And so the idea was the following, is that by applying a voltage to the pad, you can switch the polarization of this barium titanate very thin layer. But depending on depending on the value of the voltage pulse that you apply, you will switch, but you will not switch the whole area below the pad. So here you see some PFM images showing you the proportion of up to down domains, so the proportions of domains that have been switched. And now by switching the polarization, you change the resistance of the LSMO. And so here you see that you can get a very large change of the resistance, and you can repeat that for many pulses, and you can see that the change, so before we were talking of a change of an order of 3, here it's a change of 2 orders of magnitudes in the resistance. So this can also be used as a continuously tunable resistor that emulates biological synapse, and it can be seen as the hardware basis for future neuromorphic computational architectures. So okay, there are lots of other very nice examples, but this is just to motivate this lecture, and so I will start by reminding you a bit of the basis of bulk for electricity, so that then we understand what happens when we thin down to very thin films, and you will see that the 2 things that are very important at the nanoscales are the epitaxial strength and the electrostatic boundary conditions. And okay, again, there are many good references, but if you are interested in this topic, I invite you to read this book with lots of theoretical and experimental discussion of modern view of electricity and also of the nanoscale. And then once I've put, so that will be the first half of my lecture, and then I will really focus on trying to show you how we can tune the depolarization field, built-in voltage, and nanodomain structure in very thin films by using all these different parameters. Okay, yes. So bulk for electricity. I know that you've had already nice lectures on electricity, and that you had the lecture of Vanderbilt last week. But I just would like to make sure that everyone has are the same level and have the same ideas. So in ferroelectric materials, you have this ferroelectric phase transition, where below a critical temperature you have a polarization, and above a critical temperature the polarization is lost. So at high temperature you start with a central symmetric material, and when you decrease the temperature there will be a breaking of the symmetry, and this breaking of the symmetry will give rise to a different polarization. You see that the 2 different polarization states here are stable, so this is the energy as a function of polarization. So below the critical temperature, you have the stability of these 2 polarization states, and you can switch from one to the other by applying an electric field. Okay, now of course you can model it, and there are different ways of modeling it. So here, just as a reminder, and this is what you've seen with Vanderbilt, is this idea of a soft mode or model Hamiltonian. So here I'm writing the model Hamiltonian as a development in terms of psi and I think probably he used mu, but okay, it's the same. But you see that, okay, you can develop the energy as expressed as a function of the distortion of the soft mode. So what, well, the amplitude of the soft mode. So what does it mean? We said that below a certain temperature, you have a breaking of the symmetry. So you can see that the unit cell is not centrosymmetric anymore, and you have some distortion. And now the amplitude of this distortion can be expressed in terms of this. Here you see also a dispersion curve that shows you that here you have some values that are below 0, so you have negative values here, well, that are actually, well, it would be the square that is, the square of the value that is negative, so here it's written as a function of, in terms of imaginary part. And you see that you have here these soft modes that appear, for example, at the gamma point that correspond to this distortion. And the polarization can be expressed as a function of this distortion. So you take this distortion and you multiply it by this Born effective charge. So instead of just using the ionic charges of your element and the position of the different elements in your material, you also have some hybridization, some hybridization coupling here. And so you see that effectively, because of this hybridization, you might have an effective charge that is much larger than the ionic charge. Okay, so this is in terms of soft mode and model Hamiltonian. It can also be expressed in terms of the following the Landau-Devonshire approach. So here, again, I'm expressing this energy, but this time directly as a function of the polarization, which is used as the order parameter. And so when you do that, you do the calculation, so you look at the derivative of the energy, and you express this alpha as a function of the temperature. And so then you can have two different kind of transitions. So depending if this gamma value here is positive or negative. And what you see by doing simply the math is that you can, well, from this alpha you get the transition temperature, and you can get the value of the two stable polarization states. So how do they look like? The first order transition, so you have the polarization that decreases and then drops. And in terms of the energy double well, you have this kind of energy double well. For the second order, you have something like that, and you have a decrease of the polarization that looks like that. Okay, just why can we follow the two different approaches, and what are the similarities and the differences? So in the Ginsburg-Landau-Devonshire approach, this is the idea is to look at the system macroscopically and to really express everything following the thermodynamic concepts and expressing everything as a function of what we can measure, so this polarization. And all the coefficients will be fitted from the experiments. So, okay, so it works quite well. The model Hamiltonian approach is an approach that is looking at the system from a microscopic level, and it focuses on the soft mode and so these atomic displacements. And then you see that it's very similar, but the coefficients are obtained from first principles. So both approaches should give, in principle, the same result, but you see that depending on how you want to look at your material, you can feel more comfortable with one of the approach or the other. At the end, what happens is that anyway, if you remember from the previous slide, the polarization can be expressed as a function of the amplitude of this atomic displacement. So if you start with one model, you can go to the other anyway. Okay, so now that we understand what happens in bulk ferroelectrics, let's go to thin film materials. And when we work with thin films, as I said before, what is very important is the epitaxial strain. So that will be, for example, well, mostly the strain that is induced by growing your thin film on top of a substrate that will have a different lattice parameter. The other effect that is very important also, and that we will discuss, is the electrostatic boundary conditions. So let's start with the epitaxial strain. And as well, those who are growing thin films know very well, there is quite a large number of substrates that are available commercially. They all have different, here the scale is just showing you the different lattice parameters, and here on top you see the different lattice parameters of bulk films. And so of course, if you choose one material and you want to grow it on different substrates, the strain will be different. And so you see from here that you can really play with the strain in the positive or negative region. Okay, so what will happen to the ferroelectricity? If we go back here, so here I took the Ginzburg lambda approach again. So here, just to remind you how we express the energy, we have this alpha term that gives you the transition temperature and the polarization. What will happen is that because there is a large strain polarization coupling, if you do all the calculations, and I'm not putting it here, but okay, I mean you can find it in many nice books. What you will see is that actually the strain imposed by the substrate will change this alpha and gamma terms mostly. And if you change this alpha term, you see that it will directly change the temperature. And if you change the gamma term, well, if you change the critical temperature and the gamma term, you see that it will affect the polarization. So applying a strain to your material, either by a substrate or any other kind of strain or pressure or whatever, will change the temperature, the critical temperature, and the polarization. And if you do the calculation, like it was done here by Pertsev a while ago for barium titanate, what you see is that depending on, here you see the misfit strain and the critical temperature at 0, so this is where you don't have any strain, so this will be the bulk critical temperature if you wish. And as soon as you put a positive or negative strain, then you can recalculate the TC, and you see here how the TC has changed as a function of strain and other parameters here. And you see that the TC increases in both cases of strain. And when the TC increases, you also get an increase of the polarization. So these are calculations for barium titanate. And here are some very nice measurements showing you for barium titanate between strontium mutanate electrodes on different kind of substrates, so gadolinium scandate or dysprosium scandate. You see that the P-loop is different with different saturation of the polarization. So you see directly the effect of the strain on the polarization. And you see also by measuring here the lattice constant that the critical temperature happens for different values. So what they have shown here by growing barium titanate on two different kinds of substrates is that you can have a 500 phase shift in TC, so this is huge, and a 250 increase in the polarization. So the effect of strain is extremely important. So this is in barium titanate that is already a ferroelectric material, but actually you can also, by applying strain, induce ferroelectricity in non-ferroelectric materials. So here this is strontium titanate, which you know is an incipient ferroelectric and paraelectric down to 0 Kelvin. And here what was shown in this work is that it can become ferroelectric at room temperature. And so these were 50 nanometer thick strontium titanate strained on dysprosium scandate. So you can, because of the strain, from the strain effect, from this epitaxial strain, because it's an asymmetric strain also, it's inducing some asymmetry in your material and it's inducing ferroelectricity. Yes?
So not only with like a lattice mismatch, but can you also induce strain with like a difference in coefficient of thermal expansion or other ways?
Very good question. So the question is, okay, so this is with strain with difference in lattice mismatch, but can we also induce strain with difference in the thermal expansion coefficients? So it's true that if you have difference, if you have two materials that have different thermal expansions, well, usually, and this is something that bothered me for a while, usually the strain is expressed as a function of the lattice mismatch at room temperature. But once you have thermal expansion, if the two materials don't have the same thermal expansion, is one has a larger slope than the other, then the lattice mismatch is actually also changing as a function of temperature, and you are changing the strain. So yes, of course, it will have an effect.
So it's a derivative, more so.
Yes.
Okay.
Yeah. But it's true that usually, okay, when they have a graph like that where you see the temperature as a function of the in-plane strain, it's the in-plane, well, okay, we calculate, yeah, it's usually the in-plane strain that is calculated at a fixed temperature.
Okay.
So it will deviate a bit. Okay, and so what you see also here in the dielectric response, so you know that you have a large dielectric response of the material when you reach the critical temperature. And so you see here, for example, for strontium titanate on disco, that at room temperature you have this large dielectric constant. Okay, so keep in mind that strain is very important in nanoscale ferroelectrics, but electrostatic boundary conditions are extremely important as well. So let's spend some time on that. And to understand what happens, you have to go back to the origin of the ferroelectricity, and we can go back to 1959, to this paper of Cochrane, where he was explaining how where he was explaining the theory of electricity, and the idea of Cochrane was to say that, okay, you have some, you have competition between a lot of different terms, so this is always true in whatever you are doing in physics, and so you will have to consider the competition between the short-range and long-range forces. So the short-range interaction, they come from the chemical bond interaction, polyrepulsion, and so on. But then you also have to consider the long-range forces that are coming from the dipole-dipole interaction that will at some point make your soft mode appear. And so the idea is that you need to have this dipole-dipole interaction to explain that at some point the ferroelectricity will appear. And this interaction is something that is not symmetric. So when you have the dipoles in your material, they will interact with each other. And the only way to explain that at some point you will get ferroelectricity is if you gain energy by aligning these dipoles. And so if you do that, you see that you need to have a certain number of dipoles to gain this energy, and you have a coherence length that is different in this direction, so in the direction of the polar axis, and in this direction. So what will happen is that now you are gaining energy by aligning the dipoles within this volume, but if you start to reduce the size, then what happens? You are cutting here, and you are not getting enough energy from these long-range interactions anymore, and so in principle you are losing the ferroelectricity. So what can be done? And the idea at the time was that the correlation length, you see that it's around 10 to 50 nanometers, when it depends a lot on the materials, and so you see that if we are working at the nanoscale, in principle, we are killing the ferroelectricity. But now, instead of just reducing the thickness of your material, what you can do is that you put electrodes, you screen the electrode, and so actually what happens is that the material will, if you are in the perfect short-circuit boundary conditions, the material here between the two electrodes will see some virtual dipoles, some image charges. And so because they see these image charges, they feel perfectly happy because they believe that they have also all the other dipoles that you've removed are still there. And so in principle, if you put perfect short-circuit boundary conditions with perfect electrodes, there is no problem anymore. You can maintain the ferroelectricity. And so there has been some effective Hamiltonian calculations that have shown that actually under these real perfect conditions, you can maintain polarization in very thin, here just 3 unicells of PT. And so to understand that, in reality, you don't have perfect electrodes, and so how can you understand what will happen in this thin film when you cut the additional dipoles? So, okay, what you need to understand is the idea of this depolarization field. So if you have a very thin ferroelectric field, that we are considering here only a uniform polarization. The polarization corresponds to surface bound charges. Okay, so you have the dipoles and the charges at the surface, and these bound charges give rise to a field. And if you do the calculation, you see that in many cases, actually the value of this field is of the order or even larger than the coercive field itself. So the coercive field is a field that you need to apply to switch the polarization. So that shows you that if you don't do anything, you cannot maintain the polarization. And so there are different ways to screen these surface bond charges. So by putting some metal electrodes, or by using the surface adsorbates that are usually very efficient at screening the polarization, or even if you have some finite conductivity in your material, you can also screen this polarization. If you don't screen it, you will get either the suppression of the polarization, or you can have, in some cases, the rotation of the polarization in plane, because now it's not a prime anymore, because in plane the dimension is much larger. Because of this idea of also this depolarization field, you can also get, in case of multi-layers, if you have ferroelectric and paraelectric layers that are stacked on top of each other, you can induce polarization in the paraelectric layer as well. Or you can have the formation of domains that we will discuss as well. And these domains can have different shapes. The standard key-tail domain, so just up and down polarization, because then on average at the surface you have a zero charge. Or they can follow these Landau leaf sheets or even these polarization vortices that you've seen before. Okay, in terms of a simple electrostatic model, if you take here, I'm just drawing a thin layer of a ferroelectric material with a polarization, the surface charges, and because of the polarization and the surface charges, you have a depolarization field inside your material. So this is the voltage drop through the thickness of the ferroelectric layer. And so, okay, we are assuming here that that outside you have the vacuum and nothing particular happens. Now, we said that if we put some electrodes, perfect metals, you can screen these surface charges. So if you do that, here you have a perfect metal, a perfect metal. These two perfect metals will completely compensate the surface charges here and here from the polarization. And now everybody is happy because this screening will compensate exactly the field inside the material. So you will have a zero depolarization field. And so the polarization is stable. Except that in reality you never have a perfect, you cannot achieve absolutely perfect screening. So how can we model that? The idea is, again, I have here my thin film, I have no real electrodes, and so the way to express that is just saying that now the charges that are coming from these real electrodes, instead of screening perfectly, you can see the interface as a parallel plate capacitor. So that means that the screening charges do not overlap exactly with the surface bound charges. You have a small distance here that we will call the effective screening length. So it will tell you how efficient the screening is or not. And so now you have a parallel plate capacitor with different charges here, and that will give you a voltage drop at each interface. And now if you are in the short circuit boundary condition, you need to have the same voltage here and here. So each of the voltage drop here at the interface will add up and give a voltage drop inside your material. And this voltage drop is giving you a non-zero field inside your material. So we need to express this field. And so you see that, well, again, parallel plate capacitor, the voltage drop at the interface is this effective screening length times the charge, so the polarization. And so now if you have two interfaces, you just add up the two voltage drop, and the field inside your ferroelectric is just the voltage drop divided by the distance. And now you see directly that, okay, if you express it as a function of the screening length, if you have a very good electrode, you will have, in this model, it will be expressed as a very small effective screening length. So a very small effective screening length will mean a small depolarization field. So this is good. Now, what you see also is that if you have a fixed effective screening length that depends on your electrode, if you reduce the thickness of your film, so the D, the smaller and smaller the thickness of your film, the larger and larger the depolarization field. And so this is also how you can see that if you are working with bulk crystals, you can put any kind of electrode or surface adsorbates and so on. It will perfectly screen the surface charges, and it will result in a negligible field inside your material. But when you, with the same electrical boundary condition, when you reduce the thickness of your film, there will be a thickness below which it will become a prime. Okay? So this is simple electrostatic. Yes?
Just a simple question. When you do this, do you consider D as the total thickness of the film, or the lambda F.
No, so this is really the thickness of the film.
Yes, and so we add a layer which is independent.
So what we assume is that this effective screening length will be some length in the electrode.
Okay.
But it's just a way to model it. So actually here, if you look, for example, in the case of semiconductors, this is something also that you can see, or maybe not see so well, but in the case of semiconductors, what you will have is that you will have a gradient of the charge at the interface. And this gradient of the charge at the interface will also give you, so here instead of having just something linear, you see that you have something that has this shape like that. And again, because of this drop, the voltage drop here and here at each interface, it will induce a voltage drop inside your material. Yes?
Can you comment on the role of differences in work function or accumulation of oxygen vacancies at each interface and how that affects the depolarization field?
Okay, so that's a very good question. The question is on the work function and oxygen vacancies and everything. So what I like, so of course, if you know all the details of your electrode, you can you can calculate this effective screening length, and I will come back to that immediately. But what I like with this model of this effective screening length is that it's effective, meaning that you put everything inside. You don't need to know all the details of each contribution, but each of these phenomena will contribute to the effective to this effective screening length. So it's just a way to model from a bit further, if you want, to understand what happened without having to know all the details. But there are also some calculations, so I just want to mention that, of course, all this you can also do looking at the electric displacement. That is quite a useful term as well. Like I say, let's... Okay. And this effective screening length has been calculated, for example, here using some model Hamiltonian calculations. So here you see the work of Javier Unquera and Philippe Gosset, but Stengel also, and Vanderbilt and Spalding have been doing a lot of work also on these effective screening lengths. And so the idea is, using a model Hamiltonian calculation, is to calculate this potential drop at the interface between different materials. And so here you see again this potential drop. So it's not exactly linear. Again, this is a simplification, but you see that you have a voltage drop that induces a voltage and a field inside the ferroelectric layer. And what is very interesting from these calculations is that what you see here, you see the number of these effective screening lengths, but what you might notice is that, for example, here I have straws from Titanate electrode with different ferroelectric material, barium titanate, lead titanate, and even strontium titanate. And you see that for the same electrode, you have different values of this effective screening length. So again, this answers your question, because this effective screening length is taking into account not only the Thomas Fermi screening length of the electrode and parameters like that, but it's really taking into account the interface as a whole. And so the interface will be different, so this effective screening length will be different if you use the same electrode, but with different materials. Okay? And so this is quite useful, because now, depending on the kind of material, on the ferroelectric material that you are working with, you might have a good idea of what would be the better screening, and so which electrode you would need to work with. Okay, so the conclusion here is that when you work at very thin thicknesses, at the nanoscale, you will have to worry about the depolarization field, so the field that is left inside your material. This depolarization field depends on this effective screening length, so on the electrostatic boundary conditions. You also see that it's proportional to the polarization. So if this depolarization field is a prime, the first thing that it will do is that it will reduce the polarization, because by reducing the polarization, you reduce the depolarization field. And it depends not only on the choice of the electrode, but really on the pair, on the electrode and ferroelectric that you choose. Okay, so in terms, so we started the lecture by looking at the model Hamiltonian and the Ginsburg-Landau approach. In terms of the energy of your material, when you have this depolarization field, you take again the expression of the energy of your material, and you add a term that goes as minus ED dot P. So that means that because you have this non-zero depolarization field, you have an energy cost. So you see that the field here goes anti-parallel to the polarization, and so when you add this term, actually it costs some energy, so it's a positive term in energy. So again, you see easily that to reduce this energy cost, you will have to either reduce the depolarization field or reduce the polarization. And if you, because E goes as P, here that means that you are adding an energy term, positive energy term that goes as P square. So P square means that actually you can rewrite this by changing your alpha term. And if you remember what happened with the strain effect was changing this alpha and gamma term. So here you are changing the alpha term that gives you the transition temperature. And because you change the transition temperature, it will also change the polarization. So here from this Ginzburg-Landau, you see that when you have this depolarization field, you increase the critical temperature and you decrease, of course, the critical temperature and you decrease the polarization as well. So that means that, and this is why it's called the depolarization field. It depolarizes your material. It goes against the ferroelectricity, so it will reduce the temperature range over which you can have a ferroelectricity, and it will reduce your polarization as well. Okay, and just as an example, what we did quite some time ago was to look at PTO thin films grown on NB-doped STO substrates, so metallic substrates, and we looked at the tetragonality, and what we saw is that as a function of the film thickness, the tetragonality, so the C over A, so how much the unit cell is distorted, this tetragonality was decreasing as a function of the film thickness. And by discussing with Philippe Gosser, we realized that actually this decrease of the tetragonality is linked to a decrease of the polarization. So this is a strain polarization coupling. This alpha term is not the same as the alpha term in the Ginzburg-Landau, so this is why I have the tilde. But I mean, it's very simple to see that if you have a ferroelectric unit cell, so a distorted unit cell, the more distorted it is, the higher the polarization inside your unit cell can be. And so by measuring the tetragonality, you get an information on the polarization. We did it this way because the films, PTO films, are known to be very leaky, and so it's difficult to measure directly the polarization, but we measure the tetragonality and you could see this decrease that is related to a decrease of the polarization. And by doing so, and Philippe Gosset did some calculations and some fits of this data, and so he could extract an effective screening length of 0.12 angstrom. Okay, so just to finish with that, in terms of the energy double well that you have in ferroelectric materials, so this would represent the value that you have in the bulk. If you add a depolarization field, what will happen is that you make this energy double well more shallow. And so it makes sense that if you look now, you can see that with this depolarization field, you are not only reducing the value of the stable polarization, but it will be also easier to switch or to remove this polarization. And you see that this is an effect that is completely symmetric because the depolarization field depends on the polarization, and so when you switch the polarization, the depolarization field will switch as well, and so you have this effect here. But in materials, I've been talking a lot about the depolarization field. What you have also to keep in mind is that it's not always symmetric. You might have a field that is due to the interfaces, that is due to the fact that you have different interfaces and so on. And so you can also have a fixed field that is independent on the polarization. And this fixed field, what it will do, we call it the built-in field. It will favor one polarization over the other, and so it will asymmetrize this energy double well. Okay, and if you look at the PE hysteresis loop, so in red you have the initial polarization loop. If you add a depolarization field, you see that in blue what happens is that the loop is now more narrow, so it's easier to switch, and also it doesn't go as high in terms of the polarization. And if you have a built-in field, the effect of this built-in field will be to switch this P loop in one direction or the other because you are favoring one polarization over the other. Okay, so all this we've been always thinking in terms of a uniform polarization, but of course one way for the material to also decrease the surface charges, because of this depolarization field, will also be to create some domains alternating with up and down polarization, so that overall you have zero charges. And so following the Landau-Lifshitz-Kittel law that was developed initially for ferromagnetic materials, that can be also expressed for electricity, you find that the periodicity of this domain, of these domains, scale as the square root of the film thickness. So domains in thin films, we know that they are present in many, many cases. So here I'm just citing a few work, but there are many, many others as well. So for example, the work of Streifer and Fong, where they saw by X-ray diffraction in PTO thin film that you have this 180-degree domain. So these are diffraction images showing you the periodicity of the domain and the orientation of these domains. These domains could be seen also by AFM on the same PTO thin films. Again, some PFM images on bismuth ferrite, where here you can have different orientation of the polarization as well, and different kind of domains. Optical microscopy images showing in lithium niobate some very nice nucleation growth and branching in of the domains. PFM, NCAFM as well, so conductive AFM on PZT, showing 90-degree domains. High resolution TM on PZT showing this flux closure domain configuration. PFM on barium titanate, again showing this flux closure domain. Oops. TM images also with this GPA analysis that was explained very nicely yesterday by Odile, where here that was applied on PTO thin films, and using this GPA analysis they were able to also show this flux closure quadrant and the change in the strain of the PTO films. High resolution TM images on STO-PTO superlattices, where you see the vortex on vortex structure that I guess Lane Martin has shown you last week. And also some nonlinear optical microscopy on PZT, showing that you have some non-Ising and Carroll 180-degree domain walls, or LPFM and second harmonic generation on STO-PTO superlattices, showing the coexistence of vortex and ferroelectric phases. So, okay, just a few examples, but as you see from the literature, there are many, I mean, in nanoscale ferroelectrics, you have a lot of domains, different domain configuration. For a long time, we thought that the domain configuration was very simple, but now we understand also that you can have much more complex patterns like these vortices. And of course, all these domains and the domain walls will affect also the properties of your materials. And so it's important to be able to understand how you can control these domains. So again, when we work with nanoscale ferroelectrics, I said that the strain is quite important. We are growing the materials using epitaxial growth, so I would like just to mention a few things about epitaxial growth. The importance of the substrate, we've seen before, but I want to show this very nice image. So this is a silicium growth of a crystal that produces the wafers. And of course, then we want, okay, when we have a nice substrate, we want to be able to grow nicely the films on top of the substrate. So these are just a few pictures of different lab equipment. We have pulse laser deposition, molecular beam epitaxy, or RF magnetron sputtering. And so in the samples, in the work that I'm going to talk to you now, we grew all the samples using RF magnetron sputtering. So you've had a lecture already on pulse laser deposition last week. And but I'm not sure that RF magnetron sputtering has been mentioned, so I would like to just say a few words. So the idea is very simple. You have a vacuum chamber. You have different guns here inside the chamber. So the idea is that on each of the guns you have a target that contains the materials that you want to deposit in the form of a ceramic material. And then what you have to do is that you have to find a way to remove the atoms from this ceramic target and to put it on the substrate that is positioned here. And so RF magnetron sputtering works this way. Behind the target you have a magnet, so magnetron. And inside the chamber you put some argon and oxygen. And so what you do is that you apply a very high voltage and you change the argon gas, you turn the argon gas into a plasma. And so here you see the picture of the plasma. And now the argon ions, they will be attracted to the target because of the magnet. And so they will just hit very strongly the target that will extract the atoms that will fly everywhere in the chamber. And some of them will touch the surface of the substrate. And now if you have the good condition in terms of pressure, in terms of temperature and so on, the atoms will stay on the surface, will move on the surface, and will find the good position to epitaxially grow. And this is quite a slow, very slow process. It takes a few minutes to grow one atomic layer, but this allows us to have very high quality of the sample. So this is an image of the sample, and then you just need to study your sample. Okay, so we've been doing epitaxial growth using RF magnetospectrometry for a long time. Here I'm focusing on PTO, so lead titanate, that is ferroelectric tetragonal at room temperature, with a lattice parameter, well, in-plane lattice parameter of 3.904, and a C-axis parameter of 4.15. And if we work with strontium titanate, which is paraelectric cubic, the lattice parameter is 3.905. So when you grow this material on top of strontium titanate, yes?
I have a question about the sputtering. So I'm not very familiar with it, but why do you want to do it like such an off angle instead of...
This is because of stoichiometry. So we do this off axis, so the fact that the substrate is here rather than in front, so the process is much slower when you do that because you move a lot of the atoms, but then you don't have a problem of, the energy of the atoms that come to the surface is lower, and it will not, when it arrives at the surface, because it has a lower energy, it will not be removing those that were already there. So it's much more gentle for the sample. And in terms of stoichiometry, so we usually work with targets that have already the good or very close to the good stoichiometry that we want. And if you go in the direct way, it doesn't work. So this is also because we are working with oxide materials. If you do a sputtering with some metals with gold or platinum and stuff, you can you don't care because you just bombard, and if you have some species that are removed, it doesn't change the stoichiometry. But in oxide, it's very important to be in this off-axis geometry. Okay, so now when we grow PTO on top of STO, because of the nice in-plane lattice matching, what will happen is that the C-axis will be always out of plane. So then that means also that the polarization that you will have will be either pointing up or pointing down. So here we don't have any issue of having the polarization rotating in plane, because now because of the strain that you are inducing, this would cost a lot of energy. So we are using the epitaxial strain and the choice of the substrate to make sure that the polarization axis is out of plane, and so the polarization can be pointing either up or down. Okay, and here this is just to show off a bit. We've been doing lots of growth and studies of these PTO thin films or superlattices. You see this very nice high resolution, this very nice TM image showing you that we are really stacking the atoms and achieving the atomic scale control that we want. So now for the last part of my talk, I want to really focus on showing you some examples on how we can tune this depolarization field, built-in voltage, and therefore the nanodomain structure in the ferroelectric film using all these different parameters. Yes?
You grow superlattices with RF sputtering?
Superlattices with RF sputtering, this is what we are doing. So actually, if we go back to the image here, what you see is that here you have three, in this chamber you have 3 of these guns. We have chambers with 4 different guns. And so the idea is that each gun contains a different ceramic target. And so for example, one will be PTO, the other one will be STO, and here the other one was strontium Titanate as electrode. And so the way we do it, it's completely controlled by computer, is that you just start the deposition, so you open the shutter in front of one target, and so you grow, for example, PTO layers for 5 minutes, so you know that you will be having 3 unit cells. Then you stop the deposition, close the shutter, you open the other shutter, and you start the other layer. And so we are, I mean, what I've showed you here is that this PTO-STO superlattice with 3 unit cells, this was going using this system.
So you were using extremely slow growth rate,
So we use.
already know the growth rate?
Yes, exactly. Yeah, so we don't have any in-situ control, so we really have to rely on a very good calibration of the system beforehand. So what we do is that we go PTO, we go STO, different, changing the parameters. Then once we have the parameters for the good quality, we change the time of the growth, and then we just scale, then we know that, okay, to go 1 layer, you will need 1.2 minutes. And this is then entered in the program. And what is very nice with sputtering, so it's a bit painful when you start because you have to adjust and calibrate, but once it's calibrated, it's very stable. So it works. Yes?
Just a basic question here. But can you just use your parameters from one machine on another one? The same one, I would say?
So I think there was a similar question for MOCVD the other day. I don't know if it was you already or somebody else. I think it's, so the question is, can we just take the same parameters and do it in another system? I think it's like cooking. You have a recipe, you apply it, and when you do the first time, it doesn't work. But you can start from the same parameters. You can use these parameters to then adjust it and find which one are the good for your oven. so yes, and I mean, even in the group, so we built several of these sputtering systems because in all of them we grow different materials, but also, for example, we grow strontium Titanate in many of the different systems, and for each system we have to change a bit the temperature because also the thermocouple that you have to measure the temperature is not exactly at the same position. And there are things that, again, as in cooking, you don't control everything, but once it works very well. Okay, so the goal of the rest of the lecture will be to address all these issues. First, spacer layers. So the idea, you've seen the importance of this depolarization field and built-in voltage, and so the idea was to really be able to tune the depolarization field inside nanoscale ferroelectric material. And so what we did is that we took PTO thin film, we took strontium titanate substrate as I told you, we did strontium Titanate as a bottom electrode to be able to do the measurements, and then we put some very thin STO spacer layer. And why do we call them spacer layer? Because the idea is that these layers will put some distance between the polarization surface charges and the screening charges from the electrode or from the surface absorbates. And I mean, this idea was not new. It was used already before by government and co-workers, where they showed that if they were growing barium titanate thin film between strontium Titanate electrode, although the structure seems to be symmetric, what they were having is that in terms of the energies, they had this asymmetric energy double well. And so the polarization, you can see here that the polarization was stable only in one direction and not in the other. And as soon as they put 1 unit cell, I think even of the STO, or 2 unit cells of STO on one side, actually they were able to make the double well energy symmetric, and so now they had the 2 stable polarization state. This was due to the fact that adding this STO spacer layer was removing some unfavorable interface between the Titanate, so you had the Titanate oxide layer and barium oxide layer that was favoring one polarization over the other, and by putting this STO bilayer, it was making everything symmetric. So we did that with the idea of being able to change the thickness of the STO, the PTO, and see what happens. So we use PFM, so in principle you know everything about PFM now, hopefully. So just to remind you, the idea is that, okay, you come with the tip of the FM, you apply voltage, you see how the material is vibrating, either in phase or out of phase, you record the signal, and you know below the tip what is the orientation of the polarization. So again, we use this technique very much because PTO is known to be very leaky, so it's very difficult to do macroscopic measurements with large electrodes. Okay, So this is the image. If you go 50 nanometer PTO directly on top of the strontium retinate, what you see is that you don't see anything in the phase. So you have a uniform phase. That means a uniform polarization, and not much in the amplitude either. As soon as you put just 2 nanometers of this STO spacer layer between the strontium retinate electrode and the PTO, boom, domains appear. And so what you see is that in this background of up polarized material, you have some nanodots here that appear with a down polarization. And what is very nice is that from the amplitude measurements, at the domain walls, you see that you have this drop of the amplitude. Then we did the same thing with putting both a bottom and a top STO spacer layer, and we don't see any change in the configuration and the size of the domains. And if we put only a top STO spacer, we see again that we have a monodomain uniform film. So what this shows already is that by putting just 2 nanometers of STO, we do change the depolarization field. So what we are doing is that now, if you compare this one and this one, we have this spacer layer, so the screening is less efficient of the strontium retinate, so the depolarization field is bigger. So what does the film do is that it breaks into domains to compensate for the depolarization field. What came a bit as a surprise is that actually the top layer doesn't seem to affect at all the domain configuration. This might be due to the fact that during the growth already, you kind of lock the domain configuration, and then whatever you put on top doesn't change so much the configuration. Okay, then we looked at this 50 nanometer film with both the top and bottom STO spacer layer. You see, so this is just a different scale of the image, but you see again these nanodots. And so what we did is that we used PFM to write. So what we did is that we scanned with the tip of the FM over the whole area, applying a positive voltage, and then we scanned again just to read. And so by applying a positive voltage, maybe you can start to see that the size of the domain is increasing even more until it kind of merges. So if you apply a larger voltage, then you can completely switch, again, locally, the polarization. And if you apply with the tip of your FM a negative voltage, you see the effect on the domains is that the domains will shrink. So by applying a voltage, you can switch the polarization. Mostly what you do is that you start by switching the polarization at the domain wall, so you increase or decrease the size of the domains that are in a specific direction. So this was repeated several times, and what you can see also, for example, from this image, is that here the domains are bigger at the bottom of the image than at the top, and this is because we were scanning. So we applied the voltage going in this direction, going downwards, and then we were reading going upwards, and it took a while to read. So actually, while we were reading, the domains already started to switch again. And so here I'm just trying to show you two, the back switching, so how the domain go back to the original configuration after some time. So this is after writing with positive voltage, and this is after writing with a negative voltage. It's the same area, and you see that, okay, right after writing, you have a big difference in the sizes. After 17 minutes, this is a typical time for scan. 15 minutes, 2 hours, 4 hours. Oops, sorry for that. Okay, after 3 to 4 hours, you were going back to exactly the same domain configuration. So, yes?
So I just had a kind of a practical question. So for each layer, was the sample actually kept in the same chamber, or was it taken out, and could there have been some oxidation?
No, so actually it was all grown in the same chamber.
Okay.
So we didn't have to take out the system and put it back in another system. Okay. It's all in the same system, so we just all grow at once.
So then did you deposit your electrodes and wet etch them away to get the PFM measurement?
No, so for the PFM image, what I have is that I have the bottom electrode that covers the whole substrate, and then it's the tip that is used as a top electrode. But later I also have additional electrodes that were grown on top. Yes?
From the previous example, seems that when you grow on strontium retinate, the polarization tends to be down, or I don't remember. Is it a systematic thing, or is it just...
So that's a very good question. Yes and no. So what we've seen in the past is that depending on, for a specific set of growth parameters, if you change the bottom electrode, for example, if you have NB-doped STO, strontium Titanate, we did LSMO as well, depending on the kind of electrode, you can have a favored up or a favored down polarization. But then you will see later in the talk that actually by changing the growth conditions, you can, with the same set of electrodes, you can also change the favorable polarization. And all this has to do with the fact that we are changing the depolarization field and the built-in field. And so, yeah, I will come back to that later. Yes?
I also had a practical question on this slide. So how do you deal with like drift of your AFM tip, especially with these time scales? Because we have quite some drift when I'm measuring at shorter times already. So.
Okay, but no. So here we didn't have so much problem with the drifts. Here we were working at room temperature. Maybe it's becoming an issue if you work at larger temperature. I don't know. In this case, we didn't have at this scale we didn't have a problem of the drift. But I know that, for example, my colleagues who are working with the Omicron at low temperature, they have some problem. I mean, as we discussed, because you have some non-linearities in the column and so on, and some thermal effect. And then, I mean, if you're interested, I can give you the reference. They've made a small program to align actually the images. They published that, I think, a few months ago. So just remind me that I can give you the. So you can afterwards do some corrections. But here it's no correction as needed. Yes?
Could you bring the material to single domain, and if you could do it, does it switch back?
Yes and yes. So it's possible to completely switch to monodomain, and then it does switch back. And actually, I'm going to show it to you. Yeah, I'm going to show it to you on another system with a top electrode. And what is very interesting is that when it does switch back, the domains always reappear first at the same position. So it seems that intrinsically in the material, there are some places where probably you have a different built-in field. So I think that locally the built-in field is not homogeneous, and so there are some regions where it's more favorable to start, it will start to switch more easily. Other questions? No? Okay. Okay, so back switching, and it switches back to the original configuration after 3 or 4 hours. Then what's next? What we did also is that we wanted to see the effect of the thickness of this STO spacer layer. And to see the effect of the thickness, we decided to look at a series of samples, of PTO samples that were a bit thinner, because we thought, okay, it would be easier to see on a thinner sample the effect of the depolarization field. And so we have 20 nanometer PTO. The only problem is that with 20 nanometers, now the domains are, when they are here, they are much smaller because of the Kita law, and so they are more difficult to see. And so the technique that we used is that we wrote a region with a positive voltage and a region with the negative voltage, and then we compare the phase of the Asborn region to know if the sample is monodomain or polydomain. So here you see that it's polydomain because the signal of the phase is somewhere in between the signal of the up and down polarized region, and here you see that it's monodomain because the signal of the phase is the same as the region written with a positive voltage. So you don't see directly the domains, but you know that they are here because they have an effect on the phase. So all these are 20 nanometer thick PTO layers, but here it's without STO spacer, with 1 unit cell, 2 unit cells, 5 unit cells, or 10 unit cells of the spacers. And so what you see already is that without any spacer, we are back to the uniform polarization, so the sample is happy, it's creamed, it's monodomain, and when you increase the thickness of the spacer, you become polydomain. What is nice is that here you see that 1 unit cell is not enough to make it polydomain, you need 2 unit cells or more to make it polydomain. So it's not just the presence of the STO spacer layer that has an effect, it's really related to its thickness. And so what we did also is that we did some SSPFM to measure this built-in voltage, so how much the loop is shifted in one direction or the other. And so what we see is that this built-in voltage as a function of the STO thickness is changing. So what we see is that we have a large built-in voltage, so the loop is really shifted when you don't have STO, and when you increase the thickness of this STO spacer layer, you are decreasing the built-in voltage. So that means putting these STO spacer layers increases the depolarization field and decreases the built-in voltage. Okay, we also looked at what happens as a function of time. So again, this is just the measurement just after the writing of these different domains. And then we looked after half an hour, 1.5 hours, 3 hours. You see that here, the regions that we've been writing have completely disappeared while they are still clearly here. And so 7 hours, 15 hours, 30 hours. And so what we see is that you have a much faster back switching in the samples that have a larger STO spacer layer, and this is due to the fact that in these samples you have a larger depolarization field because of this spacer layer, but you also have a reduced built-in voltage. So here you have a large built-in voltage, so actually the sample is quite happy to be in this direction. Okay, so we've shown the importance of this spacer layer. I want to mention the importance of the film thickness on the domains. And what you see is that this is 50 nanometer PTO with 2 nanometers top and bottom STO. And here I'm decreasing the thickness of this PTO, so this is just 20 nanometer and this is just 10 nanometer. So the scale of the images is always the same. And what you see is that they're all polydomain but with different domain sizes. This is a Kittel law, okay, very good, it's working well. But what is very interesting also is that it's not just the size of the domains that is changing, but also the shape. So here you have really these nanodots, and then when you decrease the thickness of the film, you see that it goes more towards this labyrinthine kind of domains. Okay, top electrode. We also did some measurements by putting some top electrode. And so again, this idea is not very completely new. Here are a few examples of some work that have been done before. Here you see, so we deposited in situ a very thin transfer-mutanate layer, and then we etched. And so we came with the AFM tip on top of this electrode, but if you just apply the voltage between the tip and the bottom electrode, actually you never get a very good electrical contact between the tip and the top electrode. So you have to additionally come with a very small wire and attach it to the electrode so that you apply the voltage at the same time to the electrode through the wire, and also you still apply the voltage to the tip because otherwise you will have some electrostatic interactions between the tip and the top electrode. So we did that, and we used the PFM signal to monitor, to scan a very small region and see if we had up or down domains. And so what you see here is that we have something that is mostly uniformly polarized with a few domains. And then here what you can do is that for a given DC voltage, you can measure the proportion of up to down domains. So we start with something that is monodomain, and then what we do is that we increase the voltage applied here, and we monitor the change of the domains. And here you see that you can have complete switching in one direction, then you go back down and you see the opposite domains that appear, and complete switching in the other direction, and then you come back. And so what is interesting also is that you can repeat this many times, and what we see again, to answer the question before, is that the domains always seem to appear more or less at the same position. Also what you see is that here, if you look at this loop, this switching loop, you see that it's very much shifted in one direction. And if you compare, so this is a 50 nanometer PTO with 2 nanometer top and bottom STO with the top electrode. If you compare, if you remember from the previous slides, the same material without the top electrode, here we had something that was more centered with 50% up and 50% down domain. So the presence now of the top transfer-mutanate electrode has also an effect on the built-in field and has completely shifted the loop. So now we started with material that was polydomain, but with the transfer-mutanate, it's monodomain. And it's not just the domain configuration that it changes, but it's also the stability of these domains. So here what we realized is that as soon as we were changing the voltage, the domain configuration was instantly changing. And if we were going back to 0, it was going instantaneously within the measurements limit to the monodomain configuration. And just to show you that, what we did is that we scanned one line, so we are always scanning here the same line. This is as a function of time. And what you see, every time you see the red dotted lines, it means that we have changed the voltage, the DC voltage applied to the T. So when we start with 0 volt, you see that on this line, it's mostly uniformly polarized with just one domain that we are crossing. So it's stable with time. Then we change to 0.5 volt, and boom, you see that the size of these domains that we are scanning over is larger, and you see a small one that is appearing here. We increase the voltage to 1 volt, larger domain, and other domains appearing. 1.5 volts, it's completely switched. And then we decrease the voltage, 1 volt. The other domains appear, 0.5 volts, 0 volt. And here you see the ones that stay longer are the first one that appeared. And again, we completely switch, so they are completely erased. And we go back up, and you see that the first one that reappear are the first one that reappeared here. Okay? So again, this tells you that you have some inhomogeneities of the profile of the built-in voltage inside your material. Okay, gross temperature. So we said that we've seen, of course, that the electrodes are very important in terms of the built-in voltage and how you favor one direction over the other. But what we have noticed also is that if you take one set of electrodes, so just let me explain. This is PTO thin film with this STO spacer layer on strontium mutanate on STO substrates. So the same series as I've been discussing before. Here is that depending on the growth temperature, you can start with, okay, the pattern here instead of being a square were lines, so just to see if it's monodomain or polydomain. And what you see is that at low temperature, you have something, low temperature growth. You have something that is monodomain up. With a larger growth temperature, it's monodomain down. And in between, you have a few growth temperatures where you have something that is polydomain. And so this means that now you can favor one polarization or the other depending on your growth condition. And this is true not just for this particular set of electrodes, but here you have other series. So this is PTO on strontium mutanate without the STO spacer layer. This is PTO on NB-doped STO, and even PTO on lanthanum, on LNO electrodes. Always the same thing. You can always find a temperature where you have monodomain up and a temperature where you have monodomain down, and a set of temperatures where it's polydomain. Depending on the electrodes that you are using, you can shift a bit this temperature in one direction or the other. So this is quite interesting because then you can also decide if you don't have a choice of electrode, you can still tune the built-in field and the polarization orientation. So we've been measuring the built-in voltage as a function of the growth temperature, and you see that you have this decrease. Also, of course, we were wondering why we had this effect. And so one thing that was done at Berkeley was to measure using Rutherford backscattering spectroscopy to try to see if there is a change in the stoichiometry of our materials. And what we could see is that for different, so this is for different temperatures, you see that the average composition in terms of the ratio between lead and titanate is different. So the lead-titanate ratio, in principle, if you have PTO, it should be 1. But here what we see is that at a lower temperature, we have something that is a bit over 1. And when we increase the temperature, it goes down. So this is not a surprise because we know that lead is very volatile. So we start with a ceramic target that is overdoped by 10%. And here what we see is that the fields that are grown at lower temperature, they have a bit of excess of lead. And when you increase the growth temperature, you are losing the lead, and so you decrease this lead titanate oxide. So we change the stoichiometry. But what we noticed also from these measurements is that the stoichiometry is not constant for the field, but at, no, it's not this measurement, sorry. Okay, I don't have it here. But what we saw is that you have a profile of this lead, you have a distribution of the lead inside your material. And so so that means that you have some lead vacancies and they are not uniformly distributed throughout the material. So then we try to understand what kind of field these lead vacancies would give inside the material to explain this up to down change. And actually we noticed that for it to work, it's not just lead vacancies, but it has to be lead oxide vacancies. And so we have a profile of lead oxide vacancies that will, so you have an external built-in field because of the electrostatic boundary conditions, but inside your material you also have an internal built-in field that is not constant, okay? And so this gives you a total built-in field that is not constant throughout your material, and so now because you have this field, that will have an effect on the polarization. And what we saw is that this effect on the polarization, we don't have a constant polarization for the films, but we have a polarization gradient, and this polarization gradient, because of the strain polarization coupling, has an effect on the tetragonality of the material. And so what we saw is that we used some, we looked at the X-ray diffraction of our material, and we've been using a homemade program to try to fit this intensity profile. So this is the XRD measurement as a function of 2 theta. And what we realized is that if we use a constant C-axis for the film, it doesn't fit so well. Well, you can see, I mean, you can choose the good axis to be at the correct position, but you see that it doesn't fit so well. So the trick was to modify this program to be able to have a profile of the C-axis for the film thickness, and when we did something like that, you see that now the fitting is much better. And so we were able to see from the X-rays that you don't have a constant C-axis, you have a gradient of the C-axis, and this is related to a gradient of the polarization related to the gradient of the lead oxide vacancies. And now I'm just advertising a bit for this program. This program, if you are interested, it's completely available. You can read the publication, you can ask me to give you the program, or create a GitHub account to have access to it. This program is very nice, of course. It's very user-friendly, so I mean, that was a request of my colleagues in the labs, and so you just have something like that where you can enter all the parameters of the material that you've grown. What I mean by entering the parameters means that you can choose the substrate that you've used. You can see that you have a large list of substrates, and then you can choose the bottom layer of the different materials that you are growing, or the top layer from, again, a very long list of different materials. And you can specify for each material how many layers you've been growing and what is the C-axis, and then instantaneously it will fit, it will give you a fit. You can also load your measurements and compare the calculation to your measurements. And we've been discussing a bit with Gauthier, who is doing some very nice LVO-PVO superlattices. And okay, I'm sorry you cannot see it so well, but in less than 1 minute, we loaded the data. We entered the parameters that he thought he had for this growth. So this is a LVO-PVO superlattice of 22 repetitions of 5 layers of LVO and 5 layers of PVO, and you see that you have a very nice fitting. So if you are interested, just let me know and I will be happy to share this with you. And if you haven't seen this poster, well, that's too bad. Okay, so just to go back to what I've been telling you about the polarization profile and the C-axis measurement. So from the C-axis measurements and the profile in the PTO films, we see that we have a profile of the polarization. And when you do the calculation, you see that really this change of the polarization is really due to the charges that are coming, well, these, the dipoles from the lead oxide vacancies. So it works very well. Okay, other things that can be used to tune this depolarization field and built-in voltage are defects. And here I want to mention the work of Martin and co-workers, where what they did is that they created some point defects using focused helium-ion bombardments. It's not so they could control the density of the defects, but also the localization of the defects. And what they see is that as a function of this ion dose, they will change the polarization. Sorry, this is PZT thin films. They were able to change the polarization, so over a certain dose, the polarization is affected and decreased. And when they measured the coercive field and the imprint, so this built-in field, they also see that for a large enough dose of these point defects, they can change this coercive field and the imprint. But what I find very nice in this study, so it shows you that defects, of course, will affect the depolarization field and the built-in field, but also what they did, because they were able to bombard locally, they had a lot of fun locally implanted some point defects, right in California, I guess. And then locally it changed the built-in field. Then what does that mean? That means that they then come with the tip of the AFM, and they apply a voltage, and they can completely switch. So here it's a uniform phase image showing you that here this region has a uniform polarization. They can apply the opposite voltage, and they can completely switch the polarization in the other direction. And then they come with a voltage that is in between. And what happens is that here, the voltage, because of the built-in field, is enough to switch the polarization, but here it doesn't switch. So now, just scanning with the FM with the same voltage everywhere, they are switching one region and not the other region. And I think that's very, very nice. Okay, I think I'm not coming to the end of my talk, gosh. Can I have some additional time? No? Okay, I'm going quickly. We talked about spacer layer. We did also some intra-layers, and we also see that when you put some intra-layer inside your ferroelectric material, you will change the depolarization field and the built-in field. You will get the PDF and all the references, so please read. We did also a lot of work with superlattices. Again, some very nice images where you see that by changing the number of unit cells or the thickness of the PTO layers, you can change the C-axis and therefore the polarization. We also saw some improper ferroelectricity that is coming from really a surface effect. So that means that we've been talking so far about the ferroelectric instability, so the ferroelectric distortion. But there are, of course, a lot of other possible distortions in these very nice oxide materials. And one of them is the AFD, so anti-ferrodistortive mode, where the oxygen octahedrons can rotate in one direction or the other. And so normally in ferroelectric materials, this ferroelectric mode kills the other AFD modes. They are not compatible, except at the surface. So at the surface, it was shown that actually you can have both modes, and that actually the AFD mode will even increase the ferroelectric distortion. And so what we found is that when you reduce the thickness of the PTO, so this is an example of a 2-3 superlattice, so 2 unit cells of PTO, 3 unit cells of STO, actually you are really making a superlattice that is more a stacking of interfaces than really thin films. And so you have the properties of the interfaces that will really control the properties of your system. And what happened is this material is that we got some improper ferroelectricity, meaning that the order parameter is not the ferroelectric distortion and the polarization anymore. It's coming from these AFD rotations, and these AFD distortions are controlling the polarization. And so what we saw is that then you get a bulk polarization, well, a polarization of your device, but the behavior of this polarization as a function of temperature is different. So the classical behavior of the polarization, so this is for superlattices with larger thicknesses of PTO, it follows the standard behavior of the polarization with a reduction and disappearance at the critical temperature. But when you have an improper ferroelectric, now it's linear, and the dielectric constant, instead of having a divergence of the dielectric constant at the critical temperature, you have something that is constant. And that's a typical signature of these improper ferroelectrics. Okay, 3 minutes. In these superlattices, so before, the improper ferroelectricity was in the superlattices where the polarization was uniform. But, of course, if you change a bit the conditions, you can also have polydomains. And here in this case, we had polydomains, superlattices, and again, depending on the proportion of PTO and STO and so on, we were able to see that it's not just that they are polydomain, but actually that you have these flux closure domains between the different domains. And solid solutions. Okay, so with the superlattices changing the periodicities, the size of the different materials and so on, you can completely change the configuration of your polarization. You can also do so with solid solutions. So we played a bit, again, with the same system, the same Gauss system. And the idea is that instead of depositing layer by layer PTO and STO, we were sputtering a bit of PTO, a bit of STO, but we were changing faster than the time needed to grow one monolayer. And so we did solid solution. And then when you do a solid solution, you can change the timing and the proportion of lead to strontium. And what you see, and what you can calculate also from Ginzu and Landau, is that changing the proportion of lead to strontium is also a way to tune the TC. Here you see the TC, and also the polarization and the tetradomain. And what was really nice also with this system is that usually, if you have domains, if they are very small, you don't see them with PFM, but you can see them by X-ray diffraction where you get the periodicity from the X-ray diffraction. If they are bigger, you don't see them anymore with the X-ray because then the peaks are too close to each other, but you start to see them with the PFM. And in these samples, actually by playing with the X value, we were able to find a region where, to find a composition value where we were able to see the domains both directly from the PFM images and from the X-ray diffraction. So we were quite happy with that. Epitaxial strain. I think I've started by telling you how important it is, but one thing that I realized also during this meeting and during the poster session is that there is a very nice work of Yachi Yi in the group of Pavlo Zubko, who is removing the substrate from superlattices. And the idea of doing that is that by removing the substrate that is imposing some epitaxial strain to the structure, you will also remove the strain and therefore see how the same sample will behave without the strain and with the strain. And I see that the chairman is getting nervous. So that's the end of my talk. I'm really sorry it took so long, but I really wanted to, take the time to explain everything. I hope I convinced you that we can change the depolarization field and the built-in field by playing with many parameters. There are others, also, for example, ferroelectricity that I haven't mentioned, but you had the talk of Gustav Catalan last week. And yes, a lot of things to play with. So with this, I would like to thank you for your attention. And I would like also to thank the organizers for allowing us to be together in such a beautiful place. Thank you.